I'm going to talk about relaxation methods for elliptical PDEs or elliptic partial differential equations. And I want to introduce the idea of why we go through an iterative process in this case. So we're just going to start with a little bit of theory. I'm going to copy and paste some LaTeX that I've prepared earlier just as we go through it. So we're going to start with Poisson's equation. Del squared phi is equal to rho over epsilon naught. To make life simpler, we're going to actually do Laplace's equation. So we're going to set rho equal to naught, and we're going to assume that we're in 2D. So let me just add that little bit of text in there. So here's del squared phi equals naught equals rho over epsilon naught. If rho is 0, we've got Laplace's equation. We're going to discretize with the same uniform mesh in x and y. We're using a second order centered centered difference equation. So we have phi I plus 1j. We're using I for x and j for y. Minus 2 phi ij plus phi I minus 1j over delta x squared. That's the x differential part of the del squared. The same equivalent for y is equal to 0. Now, if we rearrange, we can find a condition that the solution must satisfy, and we find this just as phi ij is equal to a quarter times the sum of the neighbouring values of phi. If we start with some guess for phi, then this condition won't be satisfied. And the way that relaxation methods work is by seeking to change the equation from a requirement to an update method. So in this case, we'd write phi ij k plus 1, where k is the iteration, is equal to a quarter times then the sum of the neighbouring potential values at the previous step k. It's not immediately obvious maybe why we can do this. So let's just look at a way of understanding this. Let's consider just for now the steady state solution for a parabolic equation. So this is going to be written as follows. d phi by dt is equal to del squared phi. So if you put a capital D in front of the del squared phi, you'd have the simple diffusion equation. If you put a kappa over C rho, then you'd have the heat equation. But in this case, we're just leaving that coefficient to be 1. Now, in the steady state, of course, d phi by dt will equal 0, and so we'll have del squared phi is equal to naught. So what we could say if we wanted to is that in the steady state, this will give us the solution of Laplace's equation. And this is a way of thinking about the approach that we're going to be taking with the iterations. So we're going to again discretize. We're going to use a forward difference, a simple forward difference for the time derivative. We're going to use I and j for x and y and n for the time steps. And if we do that, then we get the following result. Phi ij n plus 1 is equal to phi ij n. In other words, the potential at a point at step n, time step n plus 1 is the potential at the point at time step n plus an update, which is delta t over delta x squared, and then you've got the sum of the neighbouring points minus 4 times the value at the current grid point. So this term here in the brackets is nothing more or less than the second order differential in space. And if you compare it to what we've got up above, you can see maybe what we're going to do. You can show relatively easily that the largest stable time step that you can use, the value for delta t, is delta x squared over 4. And if we substitute that into that equation, then we get the following result. And I just need to put an x here. Okay, then what we get is phi ij n plus 1 is a quarter the sum of the neighbouring grid points at the previous time step, phi I plus 1j n, etc., which is, of course, identical to this update from the relaxation method. So it's a justification of the approach that we're using for relaxation methods. Essentially, you can look at it as a time evolution along towards the steady state solution. But you should note that in this case, for the relaxation methods, what we're doing has that there is no actual significance to the time evolution in this situation. That was just a way of helping us see it. So let's write a routine. We'll update the phi, we'll take in a copy of phi, and we'll say that it's a square grid with a size of n. And this is going to be using the Jacobi method to update the phi on a grid n by n. There are, of course, other methods which converge much faster, but I'm not going to talk about them here. Inputs, we've got phi, which is potential in 2D on an n by n grid. We've got n, which is the grid size. The output is phi new, updated phi. So we're going to start by saying phi out is, let's make it actually numpy.zeros like of phi. That just sets an empty array for phi out. And then we'll do, we could do for I in range, but actually let's use numpy.roll. So we'll say that phi out is equal to 0.25 times numpy.roll of phi comma 1 comma axis equals 0 plus numpy.roll of phi comma minus 1 comma axis equals 0. So that's the x shifts that we needed, and then we'll do the y. Numpy.roll of phi comma 1 comma axis equals 1 plus numpy.roll of phi comma minus 1 comma axis equals 1. So that's our output phi, and so we'll just return phi out. And notice that this quarter times these shifts are just equivalent to these 4 points here. We will, of course, have to take great care on the boundaries. So I'm going to put that into the docstring. Note that the boundaries are not correct and need to be updated. We could set them to 0, but in this case, I'm just going to leave them as they are. Okay, so let's try this. So let's set n is equal to 15. Phi is going to equal, let's start with just 0, numpy of zeros of n comma n. That's going to be our initial potential. And I'm going to use an example that we used in the notes where we're setting the potential at y equals 0 and y equals L, for want of a better word, to 4 volts, and the same for x, but with 3 volts there. So phi of 0 comma colon is equal to 4, and phi of minus 1 comma 0 is equal to 4. And we'll do phi of colon comma 0 is equal to 3, and phi of colon comma minus 1 is also equal to 3. We should probably do the corners. We'll do that in a moment. So let me set that, and let's just plot this using imshow of phi. We'll do origin is lower, and we'll interpolate. We use a bicubic interpolation here, and we'll do a color bar so we know what we're seeing. We'll do label is potential bots, capital V. Let's see what that produces. That doesn't quite give me what I was expecting to see. Now, have I done something foolish here? So what have we got? We've got, oh, I did phi minus 1 comma 0, not minus 1 comma colon. There we go. That's why we weren't getting the potential we were expecting. So let's just look briefly at this. We've got, for y equals 0, we've got plus 4 volts. For y equals 15 or L or whatever it's going to be, we've got plus 4 volts, and then we have 3 volts for the two x limits, and in the middle we have 0 because that's how we set it up. And so what we could now do is we could try applying a single iteration of the update. So let's try that. Let's just do phi next is equal to update phi of phi comma n, and let's plot that. In fact, I'm just going to steal what I've written up here to save time. But we need to make sure that we're plotting phi next. Okay, so what happens here? Well, you'll notice actually that I didn't apply the boundary conditions that I required. So I need to do that in a second. Let's do that. Copy these boundary conditions here and do that after the phi next. The other thing that we're going to need to do is we're going to need to think about whether we can see the change just by plotting the potential. So, okay, let's apply the boundary conditions. Okay, now, if you look carefully, you might see some small change, but it's going to be much easier if we plot, instead of phi next, the difference, phi next minus phi. Okay, now what's happened? This is interesting. It's probably sensible. Let's just think through what's happening. So on the boundaries, we have 0. That's reasonable. We're applying the boundary conditions. We shouldn't have any changes. In the center, we've got 0, but that's because actually in this area, if you think about the update, you've got phi ij is going to be changed by the neighboring values, and there's nothing here. There's no changes, so of course the change there is going to be 0. And all of the change is around the edge, which makes sense because that's where we've actually updated things. So it might not surprise you that actually we're going to see a set of changes which look like, bear in mind this is a look like, not an actual physical process, which look like a diffusion inwards. So let's run this a couple more times. And you'll see that as we run it a couple more times, we're getting this sort of gradual shift inwards. Okay, so that's just an illustration of the fact that you can look at the progress of this kind of update, and it's going to take a long time to get there. So actually, our initial guess was a terrible guess because a potential of 0 in the middle when we've got +4 on y equals 0 and y equals L, and +3 on x equals 0 and x equals L. It's much more likely that you're going to have 3 or 4 in the middle. So let's change this initial guess to 3.5 times numpy dot ones. And let's plot that. And now, okay, does this make sense? Well, yes, because our color bar has changed. We've got the dark blue is 3 volts, the yellow is 4 volts. The corners are actually insignificant. I haven't set them, and they're going to just, that's not necessary. Just for the sake of neatness, let me set those to make that look prettier. But bear in mind that because of the way that the differentials work, that's not going to have any effect at all. That now looks maybe a little tidier. So that's our initial, and we could do an update and look at the change. And if we do the update and we look at the change, we'll actually see, yes, the evolution is very different. Mostly we get no change in the middle, but actually we get some kind of change around the edges. That's how we do the step-by-step update. How do we automate this into some kind of loop? Right, well, let's think about this. We're going to specify a tolerance. I'll call it tol, let's say 1 by 10 to the minus 4. We want changes to be less than the tolerance. We'll set up a maximum number of iterations. I'll set that to 1,000 just so that it can keep going for a while. Let's think about the change. So let's set an initial parameter delta is equal to 1.0, and we'll set the number of iterations equal to 1. And what we're going to want to do now is a while loop. We're going to have while delta is greater than tolerance. So we'll just put a little comment here above delta that it's this is a change, and iters is less than max iters. And we're going to want to update. So let's actually tab these in so that we have that. And I'm going to shift this into another cell because we don't want to be plotting in the same cell that we're doing our iterations. So here we have delta is greater than tol and iters is less than max iters. We perform an update, phi next is equal to update phi. We apply the boundary conditions. Let's put in a comment here. And now what do we do? Okay, well, we need to calculate delta. So delta is going to be the biggest change that's happened. We've seen already from the plots that we've got on the screen that the size of the change depends on the position in space. So what we need to do is we need to go over the entire change. So we need to think about all the points in space where the potential has changed and find the largest absolute value. Okay, how do we do that? numpy.max gives you the largest value of an array. And so we could do phi next minus phi. That would be a problem because numpy.max would give us the largest positive value. So what we need now is an absolute value, so numpy.absolute of phi next minus phi. So what that will calculate is, first of all, a 2D array showing you the change at every point in space. numpy.abs will give us a 2D array where we have only the absolute value of the change at every point in space, and then numpy.max finds the largest number. And so that is then characterizing what's happened at this iteration. It's finding the biggest change at any point in space. We now need to update the iteration number. Iters plus equals 1. And when we finished, we'll write something out. So let's do print, formatted print. Okay, finished after, see, I can't spell, iterations with largest change delta. There we are. Let's try this. Okay, it failed because I said max iter, not max iters. Okay, let's try that again. That worked. Oh, you know what? Okay, it says finished after 1,000 iterations with the largest change 0.5. That indicates that something has gone wrong. And what has gone wrong is that I've forgotten to actually make the update. So I've got phi next is equal to update phi, but I haven't then done a copy. So now let's do phi is equal to numpy.copy of phi next. Let's try running that again. And it's finished after 48 iterations. Let's plot that in the next cell. And yeah, that makes sense. We've got 3 volts where on the X boundaries, we've got 4 volts on the Y boundaries, and we have a reasonably sensible general behavior in between. We can put some contours in there as well, just to map this out. And notice that the contours need to come after the color bar, otherwise the color bar will refer to the contours. And let's do that. And now we see that we've got contours that also make sense. So you've got 3.5 in the middle. You've got some kind of general gradual shift on the outsides. So what I've done here is I started with a bit of theory just to describe why we do relaxation methods. We wrote the standard kind of relaxation method. This is the basic Jacobi method. It can be quite slow. We then set up the problem. We checked what the potential looked like. I did do a couple of manual updates and showed you what the change from iteration to iteration looked like, so you could get a sense of what was happening. Then we wrote a little while loop to explain how you perform the relaxation, and then we tested it. Just to show you, notice that we finished after 48 iterations by starting from uniform set of 3.5. What happens if we go back to the original question, which was numpy.zeros? How does that change? So here's our original. Now let's run this. And it required 289 iterations, but gives us almost the same final result. That's not quite the same, is it? But that's just because we've only converged to 10 to the minus 4. So notice that the initial guess has a huge effect on the efficiency of this. So that's everything on relaxation that I wanted to talk about today. Download the notebook if you want to and have a play.